Thanks. I'll start by thanking the organizers for this stimulating meeting. Let's see, the control. Was it here? Or? Anyways, I'll talk about work done over the last year. I apologize in advance that there won't be anything controversial in this talk. And also that the intent is to kind of have tools to answer questions we couldn't answer before. There's not going to be that much of that either. It's going to be more the foundations and how one does things. But I will make comments. I'll add comments about what I think one can do with this. There was a clicker, right? That is it missing? I can do this. I guess. Okay.
And you can, if you want to time, you can.
Okay. So this is a bit of a, I'm going to give a bit of a historical overview just to, again, illustrate some of the issues in doing this kind of work. And there was a sequence of, I don't know, maybe 20 papers back spread, but mostly the mid-late 2000s on computing numerical metrics. And of course, the reason why one comes back to that, definitely we have more questions than we had then, but the computers are very much more powerful. And so, whereas I don't think one could answer a lot of questions of direct interest before, now I think one can. So this is a few contemporaneous works. So this review, I don't think any people in this audience need much of. The examples I talk about will all be on the quintic and some variety of quintics with a lot of symmetry, the Fermat, all the way down to very little symmetry. And then I've quoted the rephrasing of the Clavial condition, which will be familiar to people here, that the two natural volume forms on a Clavial should be proportional. Their ratio should be this constant function, eta equals 1 in my conventions. And well, there's the, Yao, and then many mathematicians have rigorously proven the existence of these metrics, foundation of our field. And so, that's a question that we don't need numerical techniques to answer. But one doesn't have to go very much farther, equations where come out of string theory where, say, the warp factor can vary, certainly these cases where there are extra fields and fluxes turned on. It's not always obvious when there are solutions, and many speculations and sometimes conjectures of, well, this solution maybe produces a tachyon or a singularity and so forth. And so that would certainly be a prime application of this type of technology. So, okay, so I have another talk where I survey different numerical methods, and partly to justify the focus on this one. The thing that, if you study this, elsewhere, you almost certainly have seen is what are called mesh or finite element methods, where you have some sort of a triangulation or simplicial complex. And in our field, of course, Reggie calculus is this old and famous approach. And then, definitely one can work with Reggie calculus, and there's one point not made very clearly on the slides, which is that the difference between geometry and most problems with PDE, of course, is that since the metric is dynamical, you don't know in advance that how obviously how big, but also how many degrees of freedom a particular piece of your manifold has. And so it may be that you're in this numerical context, your discretization is allocated, one site worth of data to this area, but in the real metric, it looks like this, and it deserves to have 100 sites. And so the Reggie calculus, the simplicial methods, definitely give you a way to deal with that. You put 100 simplices there instead of one, and that's the advantage. And the biggest disadvantage is that they are really hard to program, and people just spend. There are people who professionally do this, that write code for this sort of thing, because of course it's Navier-Stokes, many important equations, but we don't have that kind of time to spend. And then the other general category are spectral methods. And I'm going to lump what we're talking about into spectral methods, where you expand your function in some sort of nice basis. And the name comes if you expand it either in a Fourier basis or it's just basis of low-lying eigenfunctions of the Laplacian. Okay, and then there are many intricacies that come in numerical general relativity, which fortunately, we'll be able to skip for maybe reasons worth discussing, but you can ask in the questions. Okay, so then the progression of the numerical works, there was this work by Hedrick and Wiseman in 2005 that really point out, this is interesting, we could do it for a K3. And they kind of use this, not literally finite elements, but a real space method where you got a bunch of points and coordinate patches, and you construct a K3 out of that. And then that's already, it's a proof of concept, but then you realize why, people that simulate, Navier-Stokes and time dependent, like predicting the weather, you need supercomputers, because if you're in d dimensions, so already d equals 4, the number of lattice sites you need, if they're all going to be equally spaced, because it's the power to the d. And so 4 is already pretty big, and 6 seems very difficult from that point of view. But the saving grace, as we'll find out in this problem, is that we actually know from Yao's theorem that the solutions are smooth. And I'll get to that, but basically that says that spectral methods should be much better. Okay, so then there was this work of Simon Donaldson, who was using these techniques to do related but different problems. In fact, to study this question, then later solved of when do metrics, when do manifolds of positive first Chern class and make Kähler-Einstein metrics. And then this is the method that a lot of work uses. And so it's a embedding method. And what that means is that we're going to, first of all, describe the manifold not in terms of some sort of complicated simplicial complex, but by equations that embed it in the higher dimensional ambient space. And then, of course, if it's a Clavial, well, that's very good, because that's how we define the Clavial. That's, obviously saves lots of trouble. But, there are several other advantages of doing that. And then what's, particularly advantageous is that if you vary the embedding or you vary the metric on the space you embed into, you can get a nice family of metrics that way. And it's not restricted to the Kähler case that I'm going to talk about. In principle, you could embed any manifold into a Euclidean space. By the Nash theorem, you can do it isometrically. And then by varying that embedding, you can get any metric. So you could translate choice of metric into choice of embedding X. Then you could also say, let's consider embeddings into higher and higher dimensional Euclidean spaces. Let's not vary X. Let's just consider a strict family of embeddings, but let's vary this metric H. And then that also gives you a family of metrics. So even constant H, although they're all equivalent in Euclidean space, once you restrict to this submanifold, they're not equivalent. And then that would have advantages and disadvantages. And of course, what we all learn in GR is that we should not picture space-time as embedded in some higher dimensional space, and that when you do that, you've introduced features which are not in the original problem, and in particular, you might introduce bad behavior in singularities. So that's the potential problem. But here again, there is some issue there, but at least we have a canonical family of embeddings, and they're the embeddings by the projective embeddings. You take the sections of some line bundle and you use those to embed it, and we know that these manifolds of interest are all ample, so there are such embeddings. And then here is a explicit family, very explicit in this case, of Kähler potentials that we could then say, let's just search for the Kähler potential in this class, which is the closest to the Ritchie-flat metric. And so if I take the z's to be the projective coordinates for the quintic on CP4, then H is a 5 by 5 Hermitian matrix. So I have 25 parameters. So I could get some kind of approximation doing that. And then to improve it, I can take the higher series, the higher degree line bundles, concretely polynomials of degree k for z instead of the coordinates, polynomials of degree k in z bar. And then I get a sequence of fixed embeddings. I've taken all the sections, so the embedding is fixed, but I can put these larger and larger dimensional families of Fubini-Studi metrics on this ambient space, this embedding space, and get more and more parameters to play with. And then this does have enough parameters to approximate the general metric. And of course, you could do this for general, hypersurfaces and toric varieties. That's not in principle harder than this. And again, it's not guaranteed that this won't produce bad behavior, but at least you haven't made arbitrary choices that could have been wrong. Okay, so it was an embedding method, and then the kind of the most interesting thing that Donaldson introduced, and again based on this other work, was what he called the balanced metric, and that term sometimes gets used for other things. But what it means here is in pictures, if you take the embedding into the ambient space, then you can visualize it as a kind of, it's just filling out this small submanifold in the ambient space. And in fact, it embeds into a round sphere in the ambient space. And that's the actual, picture that goes along with this equation, that if I take the, given the metric there, the, let's see, does this, well, this works if I want to do that. But in any case, if I, given a Hermitian metric, of course, the metric was derived from a metric on a line model. And so that's the inner product of sections in that metric on the line model. I can take the matrix of inner products of sections, and then I can actually ask that the initial metric that I proposed is covariantly equal. In this case, it means the inverse of that metric. So there's only one metric, and they gave instead of two. So that's a very natural condition. And it even sort of has a physical interpretation, because you can show that the density of states, if you think of this thing, I mean, concretely, it's the sum over the orthonormal basis of sections, absolute squared, evaluated now at a point. Okay, so that gives you a scalar function on the manifold. That's like this length that I was talking about in this sphere picture. And then this is the condition that that's constant. That's what made it a round sphere. And then you can interpret this as also like a higher dimensional quantum Hall system. The sections of the holomorphic sections are equivalent to the lowest Landau level for the U1 connection. And so then you filled the lowest Landau level, and now you're saying that the density of states is constant. And there have been attempts to connect this to other interesting physics. And anyways, the reason why it's interesting here is that there's a relatively short argument that as you consider, so this balance metric turns out to be unique for a given embedding, a given degree line bundle, and then as you increase the degree of line bundle, it actually converges on the Kähler-Einstein metric, and that can be seen from this asymptotic expansion in 1 over the number of sections or degree of the bundle. So, okay, so let me then say, I mean, why was Donaldson interested in this? And the main reason is that this is actually a very nice problem in the sense that it's convex, right? So whenever you have these nonlinear equations, of course, it's very likely that there are either lots of solutions or no solutions, and the landscape of solutions is just a very, very complicated. And then there are some nice equations where the potential, whatever however you want to define potential, this energy function, say, is not strictly quadratic, but is still convex, and then it's clear that there's either a unique minimum, or perhaps if it fails to be convex at infinity, it runs away to infinity. But there's only those options, and it's relatively straightforward to decide if there's a solution. And then that can be easily written down for this balanced metric, a functional that is convex whose variation is this condition that I wrote on the previous slide. The first thing is something that you can vary and get this inner product. And the second thing, of course, you get inverse of H. And then, it's a little work, but it's in Donaldson's paper to show that this is convex. And then the convexity means that it's not that hard to solve. And in fact, there's a very simple way of solving it, which is just to reread the equation as defining an iterative scheme. So we said, H is the inverse of this matrix of inner products. And so what you can say is, let's just compute the matrix of inner products and invert it, and then use that for a better approximation of H. And he shows that that converges when the balanced metric exists. So it's a nice method, at least from that point of view, of proving that solutions exist. And in this positive Chern class case, in fact, the solutions don't always exist. There's this condition in infinity turns into a stability condition, which has to be satisfied. And it's a numerical method. Again, it works. And Donaldson very impressively got this procedure to work with programming help from his son on some little PC. And it worked, but again, it depends what you want. If you want a Ricci flat metric, then the fact that this is not literally giving you the Ricci flat metric is some disadvantage. Okay, so then there were a number of works taking that approach, and you can also treat Hermitian-Yang-Mills with almost exactly the same stuff. You can compute scalar Laplacians in these metrics. This is an example of the convergence of the balanced metric, this function eta, as you increase the degree. And you can see even for this degree 9 or 12 or something, with the naked eye, you can see it's not quite Ricci flat. That's because of these correction terms and the expansion for the for the balance metric. And so a more straightforward thing to do if what you want is a Ricci flat metric is to just minimize the error of the metric compared to the Ricci flat metric. And then that was done by Hedrick and Nassar by numerical optimization, and then just using Mathematica to do that, in fact, what you could do in a very symmetric Clavial. And then these functionals also have some nice convexity. So again, the idea here is why I defined eta. Eta is defined in terms of the metric and the known holomorphic n form, and if you can program this functional L into the computer, then you can numerically minimize it. And the only thing which is a little not straightforward to program is the integral implicit in that expression. And then the way that we did that and subsequent work did that is by Monte Carlo. You sample 1,000 or 100,000 points in the manifold, and you approximate the integral by that. And then numerical minimization, again, if the functional is convex, is quite efficient. And then if you have this thing as a function of all of the parameters, you could actually show that these are convex as well. So that's a nice thing about this problem. Again, for the pure Clavial case, that's again the kind of thing that fails and can already be studied, analytically for the more complicated systems of string theory to understand, because it is one of the most important things you want to know is the system of equations come from a convex functional, and it was a little tricky, and even in this Clavial case, it wasn't totally obvious from the start. It's because it's related to this kind of moment map action on the space of metrics, and that would be, I don't think, something that people have really worked out for the more complicated equations of string theory. I'd be interested if anybody knows of such work. Okay, so anyways, there were these couple of methods that worked, and I think the summary of the situation is that they work if your goal is to prove that the solution exists, or perhaps for some more complicated set of equations, show that it doesn't exist. Then you want to do something like the balance metric, which is mathematically the nicest and means something even for the finite problem, right? So the discretization of the of this thing. I mean, it might mean something at the. I mean, clearly it does mean something for the finite. For metrics coming out of restricting from a finite dimensional embedding. But again, it doesn't seem very canonical. For one thing, this loss function is not canonical, and the balance metric actually is canonical. But if you want the actual Ritchie flat metric, then the balance metric wasn't it, and it's better to use these loss functionals. Okay, and then coming back to this point about why this and not some other method, then it'll be familiar that if you Fourier transform a smooth function, then the in Fourier space it falls off exponentially, and then one has the same statement for all these kind of spectral expansions. If you expand in power, the successive eigenfunctions of the scalar Laplacian, that you can show those coefficients fall off, according to the degree of smoothness, so exponentially for a smooth function and so forth. And then that's good. The then potential problem is that because you're at some finite order, you can only represent structure down to some particular scale. So naively, and it's kind of true. If you have a kth order polynomial and the overall diameter is 1, you could represent structure down to some scale 1 over k. And then clearly by varying complex structure, you could make small cycles and produce structure on smaller scales that this method would not be able to see. Okay. So that's a potential problem. And that's kind of the problem that we'll find that there's some interesting machine learning solution to. Okay, so let's various subsequent works, let me tell you the solution to that problem. So what we're going to do, and you probably wouldn't think to do this unless you've been reading lots of machine learning papers, is replace the expression for the Kähler potential, remember your log of sum of h, c, z bar, with the output of a neural network. Okay, and so what is that? Probably almost everybody here has seen that, but let me quickly review it. So the standard feed-forward network is a series of, it's a space of nonlinear parameterized maps that you build by iterating product of two kinds of maps. So there's linear maps W, just multiplying by a matrix, and then there's some fixed nonlinear map theta, which almost always, and certainly for us, is going to just work component-wise and apply some nonlinear transformation. And for us, it's going to be z goes to z squared. And then you just iterate that back and forth, and the parameters are the matrix elements of these W's. And so that is the feed-forward network that so famously can recognize cats and dogs and solve all these problems of machine learning. Okay. So in engineering, you most commonly use this activation function, this nonlinear function theta, which on each component of the vector is it's called relative. It takes positive x and it's the identity, negative x it gives you 0. So it's a nonlinear in this very minimal way, which is obviously very efficient on a computer, but actually suffices. And you can show that any function can be arbitrarily well approximated, even by a 2-layer, even by a W1 theta W2. But then you need exponentially many units to do it. And as you increase, just have a few layers here, you can actually get efficient approximations for this huge space of interesting functions. Okay, so then there's this interesting kind of, obviously, this idea of using this to represent the function that would solve a PDE is a pretty obvious idea. And there is a sizable activity in applied math studying how this works for different equations. And I'll conclude with how well it works for us. And I think it's consistent with what's known for these other equations. Okay, so how do we use that idea? So basically, we're going to replace this expression with a neural network with theta equals z squared. And we're going to take, in the first instance, there are two definitions that we compared. And the first one is this, where f is the kind of network I talked about. The inputs are, let's say, the values of the projective coordinates. We're representing a function. We're representing the point by its coordinate values, and they're complex. And so everything here is complex. And then we know that we need to get out a section of the right degree line bundle. In concrete terms, we need something homogeneous. So it had better be that that function theta, the nonlinear function, is homogeneous, and that's clearly the simplest choice. And then that defines a subspace, a nonlinear subspace, not a linear one, but some nonlinear submanifold of the space of all of the Kähler potentials of that same space that I talked about before, but with fewer and, in fact, an adjustable number of parameters, because we can freely vary now the dimensions of these intermediate vector spaces in here. And so by doing that, we can take them large enough to get as many parameters, enough parameters to fit the arbitrary function, or we can reduce the number of parameters. So it's a kind of a flexible thing. And then the other choice is to say, well, we know we need a real valued Kähler potential. We in some sense need a bihomogeneous function instead of constructing these homogeneous these holomorphic sections and then taking a square. Let's just construct the bihomogeneous combination from the start. So we could take the same flavor of network, feed in the matrix Zi, Z bar J. So that's effectively a 25. It's Hermitian. It's a 25 real, dimensional real matrix, and then feed it into a real network. And then you can check that taking theta to be z goes to z squared, you clearly still get a homogeneous, bihomogeneous function at the end of the day that you can use to construct a Kähler potential. So they both kind of a priori seem reasonable, but a little thought will show you that, in fact, the first one's not very good and the second one is good for this problem. And basically the issue is that even to represent simple things, like powers of the original degree 1 Fubini-Studi metric, this homomorphic guy, you need all the sections and intermediate layers, and so you need a lot of these intermediate dimensions to be large and lots of parameters, and so you haven't gained that much. Whereas in this second description, you could just take the original, like ZZ bar, right, the Kähler potential log ZZ bar, and then you could square it. You could take it to the 2 to the k power by just running it through a network of width 1. And so that's clearly gained you something. A very natural metric has been reproduced by a very small neural network. Oh, yeah. And, then that was that, again, we didn't quite realize that when we started, but looking at the numerical results very quickly showed that that was the case. And, then you can make other exercises to see what's the expressive power. Another test of this would be to say that from the definition, it's clear that if the number of layers in the network is d, then the degree of the resulting line bundle is 2 to the d. So you get this very rapid growth in degree. But then you say, well, okay, I was trying to use that to represent structure on the scale 1 over 2 to the d. Can I, in fact, do that? And so then you can test that by asking, can I represent this kind of peak section just for some fixed w dotted into z raised to the highest possible power? And, again, the answer is yes, it's really very easy to represent that with the holomorphic network just by adding one more intermediate variable and to add that into, the other answer. So it's an expressive thing. You can represent both, the structure on the big scale, some sort of simple metric and the high power of that, plus little corrections to it if that's what you need to represent a 3-sphere or something. And then just for concreteness, here are some examples. And then again, compared to that original prescription with depth with k equals 2 to the d, clearly this has a much reduced, and in fact, logarithmic number of parameters now scaling logarithmically in the degree. So we can, in principle, do much better. And then that raises this very interesting question. It's true, this metric, this network can be made to represent lots of structure with relatively few parameters, but now for the actual Ritchie flat metric that you want to make, is that the case, or do you still need just as many parameters as you would have needed with the real prescription? So that's kind of the, if you're interested in this from this point of view of just making the thing work well, as a numerical or applied mathematician, that would be the natural question, and I'll say what I think about that. Of course, for us, the more natural question might be, well, I don't care if it's so accurate. Is it reliable? Is it the case that if it tells me there's a solution, there is a solution, and if not, and I can control the error. So that's related, but not the same question. Okay, so that's the setup, and then it turns out to be really very straightforward to implement this. I won't go into any details, but the way the problem was set up, it's exactly a supervised machine learning problem. Basically, you look at this problem of setting the two volume forms equal to each other, and what you say is that that's like fitting a function in a data set. So the data were these sampled points on the manifold, and the target, the thing you're trying to fit, is the holomorphic volume form, and now you're trying to choose the Kähler potential that produces a metric that best fits that. And again, it may take a little thought, but you realize that this is what this code is already built to do. You just need to add a couple more functions to the code. And so the code is really quite short, and it's available on GitHub. And it's something you can configure, to add your own things. Okay, so I only have a few minutes. Let me skip some of these comments about the actual, quality. Here's something sort of interesting. So the way we tested this idea that you could represent structure on the small scale was by considering various choices of complex structure moduli. So in particular, we had these kind of complicated things like this. Okay, we've got two parameters, but we just came up with a kind of random thing that broke all the symmetries except the Z2 if you have real parameters. And then that's the advantage, basically. The previous methods, they worked if you had this very symmetric manifold, but this one works for any manifold. And now you tune the parameters and you ask, as the 3 cycle shrinks, how does the error behave? And then that's, to literally compute the area of 3 cycles, not so easy, but this turns out to be a very good approximation to it, which is easily computable. And then in this slice of the moduli space, that's how that variable looks. And then you can look at the error as that depends on the size, basically, of the 2 cycle, the distance to the discriminant locus. And without going into details here, you can see that these things do reproduce the same error as the full, the network, not the network, but the original prescription with all the parameters. But it turns out that in the case where you really need to reproduce singular behavior, you need just as many parameters. Okay, so the tentative answer was that, well, yes, it's very flexible. If you don't need all that resolution to describe your solution, you can dial back the parameters. But in some cases, you do need all that resolution. And there's not some sort of magic where the thing, magically reproduces it. And then there's, you can try to study this, more theoretically. Okay, so then an example of a question you could ask where there's not really good techniques otherwise is say something about geodesics on this, in this metric. I certainly don't know. I mean, basically the technique is that, if you have like a symmetry, like the one that you use for finding special Lagrangians, the fixed point of a real involution, sometimes you can say things on very symmetric manifolds about geodesics with symmetry, but that's it. We don't have any control over the metric to say anything else. But you can say one thing locally, which is that if you do find a geodesic, and then you look at the second variation, the Jacobi operator, it's either going to, it's the smallest eigenvalue is going to be non-positive, and that's because the sum of the eigenvalues is basically the trace of Ricci, which is 0. And so there's never any physically stable geodesic. And then this is a little paradoxical, okay, that these models clearly do have winding states. You can look at like the Gepner model, and you know, it's got things that look like winding states in it, and you need them for modular invariance. But now I've just told you there is no stable string that you could actually quantize around to get the winding state. And that paradox is still open, but what I think is the resolution is that you take a geodesic with, say, you know, it is a geodesic, it has to have at least one negative mode, but there are some basic guys with one negative mode, and then they kind of, you know, there's, you know, one-dimensional trajectory where they oscillate like this. It's kind of like a breather solution. And then that thing is the basic winding state. And then that would be interesting to exhibit one of those and see if you can, you know, look at its spectrum and at least compare with, you know, Gepner or other arguments. So that's the goal of a project that we're doing now with this metric. So these are examples of simpler geodesics and numerical metric to test it. And I'll stop there. You know, you can ask other questions, but I can talk about that in private if people are interested. So thanks. Right. Well, the basic choice we made, of course, was this, you know, holomorphic versus bihomogeneous, and that's sort of architectural, and that made a big difference. And you know, it's again, I don't see that this problem has enough structure, but maybe it does. You know, maybe it would turn out if you had some, you know, qualitative picture of what the metric looked like, you could somehow adapt the architecture to that. That'd be a totally wide open question here. We didn't go into it. Yeah. It's certainly interesting thing to explore. Yeah.
So for this nonlinear function, you just use the set squared, right?
Yeah.
How do you know what to pick? Does it highly depend on what you pick?
No, it doesn't depend that much. You know, again, it has to be homogeneous for this thing to make sense because we're feeding in, you know, we need to get out a homogeneous section. And then, yeah, you could try Z cubed or something, but it seems like that's not buying you anything.
But what about C squared e to the something?
No, it's not homogeneous.
But if the homogeneity drops out of the exponentials, you take a quotient in the exponential.
Well, okay, same comment, you know, this is all virgin territory. It sounds kind of weird to me, but, you know, maybe. Yeah. Well, again, just because it has a fibration with singularities doesn't, you know, usually the metric is smooth. I mean, you know, again, there's a lot of problems that you could formulate other equations, you know, similar equations. I looked a little bit at, you know, trying to do spectral Lagrangian fibration. And then we know, in general, we do get systems with singularities. And I think, you know, again, I think from the point of view what I'm saying here, really the question would be, what's an efficient test that you're developing a singularity? Because if you know you are, then you almost certainly do want to put in something special, you know, knowledge of what the singularity looks like to properly deal with it. But you know, again, in this case of the shrinking 3 cycle, we just tested the curvature, this eta, you know, and how accurate the solution was. But definitely there could be some finer test about what's going on near the singularity. But you know, the general message would be that yes, there's nothing special about this equation. You know, any system of equations, you know, especially, I mean, if you can write it as varying an action, then you have this advantage that you can do numerical. Well, if it's the minimum, I should say. If it comes as minimizing some sort of action, then you can do it directly by this method. And obviously, there's, you know, I think not every equation for us, they all come from actions, but of course, some of them it's not a minimum of an action, and that's an interesting separate issue. But more or less, all the equations that we study could be studied this way. We've talked about it, and we haven't done anything. Again, I think at this point, okay, the question was, how about looking for non-calibrated cycles and what's like the minimum volume as a function of moduli, perhaps, or, you know, looking at different cycles in the manifold. And yes, that would, in principle, be, I mean, what you would have to do, of course, is you would probably have to, you might have some guess as to what the cycle is, and then it's just, you know, plug and chug. Or you might have to search for the cycle, in which case you set up some more general code that you know, describes just the cycle by points on it and estimates its volume, and then starts to minimize that. That's the kind of thing we were doing for the, in fact, for the geodesics. And again, all relatively straightforward, not even that much programming, because it's so similar to what people already do with machine learning. So yeah, again, you know, good, many too many questions for you know, one group to work on. You can download the code. You know, we can advise you how to use it. Yeah.
How about the eigenvalues of Laplacian?
Yeah, that was studied by Anthony Ashmore in particular, and that's right. That's a good problem for this type of method.
So particular situations where you are
yeah.
on the boundaries of moduli space.
Yeah. Well, I must admit I didn't study his work carefully to remember if he saw something. Again, we didn't closely look at that. I mean, again, lots of things we could discuss you know, in private. Yeah. 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 I mean, basically, you want like a laptop with a GPU, and then you can do useful stuff. That costs you know $1,000, you know, $2,000, and then a very like a 1% accuracy run on this quintic with no symmetry would take like a day. You know, so it's you know, and if you don't need that accuracy, it can be faster. Yeah.